Hi students, in this session I am going to explain regarding acidic nature of phenols by taking few examples, which is very important for any competitive examination. So at first we can take basics regarding acidic nature of phenols, and then we can take few examples regarding arranging different compounds or different phenols in their increasing or decreasing order of acidic nature. So let us start with the concept regarding acidic nature of phenols. So at first, if we take phenols acidic in nature, we can confirm that by taking two reactions. We can take first reaction with sodium, and second reaction we take with sodium hydroxide. Right. If we take phenol, upon reaction with sodium metal, it forms sodium phenoxide, and along with sodium phenoxide we'll get hydrogen gas evolved. And we already know, if we get hydrogen gas evolved when a substance is treated with metal like sodium, the substance taken should be acidic in nature. So we got a general reaction, right? Like acid plus metal like sodium, it forms salt and hydrogen gas will be evolved, right? So what this reaction confirms now, if we are getting hydrogen gas evolved, along with that we're getting salt, right, like sodium phenoxide, this reaction confirms that the substance taken, that's phenol, is acidic in nature. So this is the first reaction which confirms phenol is acidic in nature. Let us take second reaction now. If we take phenol upon reaction with a base, so base taken is sodium hydroxide, it forms sodium phenoxide or sodium phenate. Along with that we'll get water. Okay, this is also a simple reaction. We can take acid base reaction, right? It results in formation of salt and water. So we are taking reaction with the base sodium hydroxide, and we are getting salt and water. So if we are getting salt and water, the base should be allowed to react with acid, right? So we are taking phenol here, it has to be acidic in nature, then only it results in formation of salt and water. So this reaction also confirms phenol is acidic in nature. So these two reactions confirm that phenol is acidic in nature. Okay, let us go to the next part now. If we take acidic nature of phenol, if we take C6H5OH, and upon ionization it results in formation of phenoxide ion and a proton H+. If we are calling phenol as a acidic compound, it means it should be able to release the proton easily, right? Or we can take like we need to confirm here what you're getting ion, phenoxide ion should be more stable compared to phenol. Okay, that we need to confirm. So we can take in other words like okay, phenol is acidic in nature because upon ionization it results in the formation of more stable. Okay, why we call this as more stable? Because of phenoxide ion is resonance stabilized. Okay, so resonance stabilized phenoxide ion is more stable compared to the phenol. So if you're getting more stable phenoxide ion, then ionization is easy, right? That's the reason why we take phenol is acidic in nature. Okay, we can confirm phenoxide ion is more stable compared to phenol by taking its resonance structures. Okay, so in the next slide I had taken resonance structures for both phenol as well as phenoxide ion. Just to see the resonance structures now. The first one, this is resonance structures for phenol, and second I had taken for phenoxide ion or phenate ion. If we see resonance structures or number of resonance structures, in both the cases phenol and phenoxide ion is the same, right? They're having same number of resonance forms or resonance structures. Now how to identify which one is more stable among phenol and phenoxide? So we can see the first resonance structures here. If we take C6H5OH and see few resonance forms here, just let me round it now. The oxygen of phenol getting positive charge, right? You can see in 3 resonance structures oxygen is getting positive charge, Whereas in the case of phenoxide, oxygen is having a negative charge, right, in two resonance forms. Okay, so this one point enough here to get idea regarding stability of phenol and phenoxide. We already know more electronegative atom like oxygen, and if it is having positive charge, that should be highly unstable species, right? So you can see phenol, three resonance structures are having positive charge. Okay, in that oxygen is having positive charge. So what you can write, the conclusion is what? The species is highly unstable. Okay, so what you can write then, phenol is less stable compared to phenoxide ion, okay, in which oxygen is having negative charge, okay, in two resonance forms. So there is a delocalization of electrons in both the cases, but if you see the charge on the oxygen, we can confirm that phenol is less acidic compared to phenoxide, sorry, less stable compared to phenoxide ion. Okay, so that's the stability regarding phenol and phenoxide ion. Okay, next one now. We can take effect of electron withdrawing group and electron donating group on acidity of phenols. So we have taken simple phenol, right, till now. Now if we take substituted phenols, and you can take substitution by any electron withdrawing group or electron donating group. So we know examples, right? For electron withdrawing group, we can take the best electron withdrawing group is we can take it as NO2 nitro group, right? That's electron withdrawing, or you can take cyanide group, right? Many examples for electron withdrawing groups. And for electron donating group, we got example, we can take alkyl like methyl. So we can take what now? Substitution, or can take substituted phenols. One is presence of electron withdrawing group, and second one presence of electron donating group. Now if you're having electron withdrawing group, what it does? Okay, so we can take a phenol, or can take like acidity of phenol. We can compare to the stability of phenoxide ion. If we are having electron withdrawing group present, what it does now? Electron withdrawing group will take electron from the phenoxide ion, right? And if it takes electron from the phenoxide ion, it is actually making that more stable, right? So what it does, electron withdrawing group, it will stabilize the phenoxide ion. And if phenoxide ion getting more stable, we can take what? Electron withdrawing group will increase the acidic strength. So if we are having electron withdrawing group present, it will stabilize the phenoxide ion, and if it stabilizes the phenoxide ion, is actually helping for ionization, right? So it will be easy ionization if we are having electron withdrawing group present, okay? And if we take easy ionization, so that's nothing but more acidic nature, right? Or acidic strength will be more. So the general conclusion is what now? If we are having electron withdrawing group, that will increase the acidic strength of phenol, okay, right? Now if we take electron withdrawing group in three different positions now: ortho, meta and para position. So remember, if you place electron withdrawing group in ortho and para position, there will be more effect, okay? So it will stabilize the phenoxide ion to the greater extent compared to when it is attached to meta position. So you can see this point here, effect is more pronounced when electron withdrawing group is at ortho and para position, okay? And the reason for this we'll get from or by seeing the resonance structures. You can see in phenoxide ion we got few positions are electron rich position, right? Just see observe the resonance structures there, second, third and fourth. You can see ortho is having negative charge, right? Electron rich. Para is electron rich, and ortho position. So ortho and para positions are electron rich position, okay? And when you place electron withdrawing group in ortho and para positions, it will be more effect, okay? Electron withdrawing effect in such positions. So effect is more pronounced when electron withdrawing group is at ortho and para position. right? This is regarding electron withdrawing group. Now if we take electron donating group, what it does now, phenoxide ion is already electron rich, right? It's having more electron density, and if electron donating group is present, what it does now, it will donate electron, right? Like methyl, it gives electron to the phenoxide ion, and if it gives electron to the phenoxide ion, it is further destabilizing the phenoxide ion, so it's making phenoxide ion less stable. And if phenoxide ion is getting destabilized, we can relate to the ionization also, right? If we are getting less stable phenoxide ion, there will be less ionization, right? Or can take acidic strength will be less. So what it does now, electron donating group decreases the acidic strength. So if you're having any electron donating group like methyl or ethyl or any other electron donating group on phenol in any position, ortho, meta or para position, that will decrease the acidic strength of phenol. Okay, now if we take generally comparison between phenol, then substituted phenols, okay, one having electron withdrawing group and other having electron donating group. So what you can write now, the most acidic will be the phenol having electron withdrawing group, right? Then comes, we can take phenol, simple phenol, and after that we can take substituted phenol with electron donating group. So that will be the acidic nature. Remember, phenol having electron withdrawing group will be more acidic, okay, right? So that's regarding effect of electron withdrawing group and electron donating group on acidity of phenols, right? Next bit is, okay, we can take few examples now. I have taken a set of 3 examples, okay, to make it easy actually, okay, or make you understand better regarding acidity of phenols. Okay, the first set of example is I have taken phenol with nitrophenols. Nitrophenols, you can take like orthonitrophenol, metanitrophenol and paranitrophenol, right? So just compare 4 compounds now. So I have taken phenol first, then all these 3 are having NO2 group present, right, in ortho, meta and para position. And we already just now we got, right, if we are having any electron withdrawing group, that should be more acidic, right? More acidic compared to simple phenol. So orthonitrophenol, metanitrophenol and paranitrophenol should be more acidic compared to simple phenol. So simple phenol should come at last, right? So you can see this is at last, okay? So I had taken decreasing order. So least acidic will be phenol. Let us go to the next part now. Orthonitrophenol, metanitrophenol and paranitrophenol, we need to compare among these 3 which one is more acidic in nature. Okay, so the most acidic will be paranitrophenol. If we take paranitrophenol, NO2 group is an example of electron withdrawing group, okay? And if it is electron withdrawing, nitrogen, we got right here carbon nitrogen bond, and if we take carbon nitrogen is more electronegative compared to carbon. So what it does then, it withdraws electron, right, towards itself, so it exhibit -I effect due to difference in electronegativity, okay? If we take -I effect, along with -I, it exhibits even one more effect also. Remember, when you place NO2 in ortho and para position, it will be showing negative resonance effect also, okay, because ortho and para positions are electron rich positions. So what it does now, in or if you take paranitrophenol, the 2 electron displacement effects are -I and -R, okay, right? Now if you take -I and -R, both are withdrawing right now, withdrawing in nature, and if both are withdrawing in nature, so what it does then, it makes phenoxide ion most stable, right? That's the reason why we got paranitrophenol is most acidic in nature, okay? Now just see the orthonitrophenol. So in orthonitrophenol also we got -I effect present, right? And in ortho position also we'll be having -R effect. So like para, we got orthonitrophenol also having -I and -R. Now how to select, okay, among these two now, right? Para-nitrophenol and ortho-nitrophenol. I taken para is more acidic in nature, not ortho, right? But they're having same electron displacement effects, okay? Minus I and minus R, okay? So remember, para is more acidic than ortho because in ortho-nitrophenol we'll be having, you know, this NO2 and this OH. Hydrogen of this hydroxy group is involved in intramolecular hydrogen bonding. So what it does, oxygen of this nitro group and hydrogen of this OH group involves in intramolecular hydrogen bonding, and that's the reason why the hydrogen cannot be released easily, okay, compared to para-nitrophenol. So it is slightly less acidic compared to para-nitrophenol. Okay, so first is para-nitrophenol, then comes ortho-nitrophenol, and the third one is meta-nitrophenol. Okay, if you take meta-nitrophenol, you know, NO2 placed in meta position, there is no resonance possible here, right? No R effect, so it's only one. That's due to difference in electronegativity, okay, and the effect is minus I. So we got only one electron withdrawing effect or displacement here. That's the reason why it is having least acidic nature or least acidic strength compared to other ortho and para-nitrophenol. So the correct order of acidic nature or decreasing order will be para-nitrophenol more than ortho-nitrophenol, more than meta-nitrophenol, and last one is simple phenol. You can just confirm it by taking pK values also. 7.1 in the case of para-nitrophenol, you know, this is least value, and if you take least value of pKa, it should be having highest dissociation constant, or we can take in other words highest acidic nature. Okay, the second is having 7.2, third meta-nitrophenol is having 8.3, and phenol is having 10. So these values confirm the acidic nature of these four phenols. Okay, this is first set of example. The second one now is phenol with orthocresol, metacresol, and paracresol. You know, cresol is nothing but methyl derivatives of phenol. So I take an orthocresol, metacresol, and paracresol compared to phenol. Okay, so first again you can take similar to the previous one, right? If you compare phenol with cresol, you know, in cresol we got presence of methyl, and methyl is an example of electron donating group which will destabilize the phenoxide ion, and if it destabilizes phenoxide ion, or I can take in other words like it will decrease the acidic nature of phenol. So if you compare phenol with cresols, phenol should be having more acidic strength compared to cresols. So I taken first one is phenol here. Okay, phenol is more than. Now compare among three here, three isomers: orthocresol, metacresol, and paracresol. Okay, so if we take methyl in meta position, okay, this is the order actually I taken, right? Now I'll explain why this is the correct order. Okay, so phenol, we got methyl group in meta position, and if we take methyl in meta position, it exhibits plus I. You know, alkyl is an example of electron donating, right? So the electron displacement effect will be plus I. Now if it is in para position, what you can take, you know, para means again para and ortho are having negative charge, right? So if they're having negative charge, we'll get one more effect called hyperconjugation. So in para methyl phenol or paracresol and orthocresol, we'll be having two effects there. Okay, one is plus I, this is common in all three. Along with that, it exhibits even hyperconjugation also. Okay, now if it exhibits hyperconjugation, you know, hyperconjugation in the case of phenoxide ion, it actually destabilizes the phenoxide ion. Okay, so if you're having hyperconjugation, it will destabilize the phenoxide ion. Okay, and if it destabilizes phenoxide ion, it means it should be having less acidic nature or acidic strength. So we can see, right, in para and ortho we got hyperconjugation, so these comes at last right here. Okay, so there is no hyperconjugation in the case of metacresol, so it comes second in the list. Okay, because only plus I effect is operating in this. Okay, so only plus I, it comes second. Now among third and fourth, why we take paracresol more acidic compared to orthocresol? You know, in both we got same effects, right? Plus I, hyperconjugation. Here also plus I and hyperconjugation. Okay, but we take para more acidic compared to orthocresol. So the reason for this, as you know, plus I effect or inductive effect, right, generally depends on the distance also, right? So if I ask here the methyl in para position and methyl in ortho position, so in which case we'll get more plus I effect. You know, plus I effect, as I said, depends on distance. If it is close to the group, what it does is the effect will be more pronounced, right? You know, in the case of para, it is far away, right, at the highest distance, whereas in the case of orthocresol, it is closest, right, to the hydroxy group. And if it is closest, there will be more pronounced plus I effect, right? Or plus I effect is more predominant in the case of ortho effect. Okay, sorry, orthocresol. Now if we take plus I effect more effective in the case of orthocresol, so what happens then? If we take more electron donating effect, it will be having less acidic strength. So the conclusion is what now? Paracresol will be having more acidic strength compared to orthocresol. Okay, because of methyl is close to the hydroxy group, and then there will be more plus I effect, okay, than in paracresol. Okay, so the right order will be phenol is more acidic compared to metacresol, metacresol is more acidic compared to para, and para is more acidic compared to orthocresol. Right, you can just confirm the values there. 10 for phenol, right, then 10.09 for metacresol, paracresol is having 10.26, then orthocresol is having 10.287. so the values are increasing, right? So if values increasing in this way, so if the values of pK increasing, then values of K will be decreasing. Okay, and if value of K is decreasing, we can take decreasing in acidic strength. Okay, this is the second example. Now the third example, I have taken methoxy derivative of phenol with phenol. Okay, just see here, we got orthomethoxyphenol, metamethoxyphenol and paramethoxyphenol. Right, so if we take methoxy group, it exhibits two displacement effects, right? Electron displacement effect. They are, one will be, you know, if you take methoxy group, OCH3, you know, oxygen will be, or can take, is more electronegative compared to carbon. So what it does, it withdraws electron towards itself. So it exhibits first as a minus I effect. And if we place methoxy in ortho and para position, it can even donate electron to the ring, right, or phenoxide ion. So it exhibits along with minus I will be having plus R also. So two electron displacement effects possible, one is minus I and other is plus R. Okay, so you can see here they are contrasting, right? One minus I means like electron withdrawing, and plus R, it is giving electron. Okay, so we can't generalize like electron withdrawing or electron donating. We need to see the position also, position of methoxy. Okay, as I said, if methoxy is present on or attached to ortho and para position, then only it exhibits positive resonance effect. Okay, and if it is in meta position, there is no resonance possible, it exhibits only minus I. Now if you take minus I, you know, electron withdrawing, right? So if you're having electron withdrawing group present, we already got, right? If you're having electron withdrawing group, that will increase acidic nature, right? So the most acidic compound among these will be meta-methoxyphenol. So that's the first one, because of minus I effect of this methoxy group. More than. Next will be phenol, right? Why you take phenol? Because the next two compounds, methoxy is attached to ortho and para position, right? And ortho and para position, if you are having methoxy, it exhibits positive resonance effect also. So because of plus R, that will act as electron donating group. So that should be having less acidic strength compared to simple phenol. Okay. So the first one will be meta-methoxy phenol, more than phenol. Right. Now just see the last two compounds here. We got orthomethoxyphenol and paramethoxyphenol. Electron displacement effects are, minus I is possible here, right, because of difference in electronegativity, and plus R, so it can give electron to the phenoxide or phenol. So in both the case we got minus I and plus R effect. Okay, now how to identify in which case, or can take which compound among these two will be more acidic in nature. Okay, now just see the first one, orthomethoxyphenol. Methoxy group and hydroxy both are bulky groups, right? And if we take bulky groups present, there will be steric hindrance, right, or repulsion between these two groups. And as a result, as a result of repulsion, what happens in methoxy, this group is slightly deviated from the plane, so it's not exactly in the plane. Okay, so if it is not exactly in the plane, what happens then? It will disturb to the resonance, right? If it is not in the plane, there will not be resonance possible. Okay, so if there is no resonance or proper resonance involved, so in that case what you can write then? If no plus R effect, okay, or can take slightly less positive resonance effect, more minus I, minus I nothing but we can take like electron withdrawing. Okay, so electron donating is less here, okay, compared to para. In the case of para methoxyphenol, there is no repulsion, right, because they are far away. So what happens then? There is easy delocalization possible. Okay, so it can give electron very easily to the phenoxide ion. If we can give easily the electrons, it means it is destabilizing the phenoxide ion. Okay, and if phenoxide ion is getting destabilized, that should be having least acidic strength. So para methoxyphenol is least acidic, okay, among these all four compounds. So remember why orthomethoxyphenol is more acidic, because of slightly reduced resonance, because of different planes, right? And why you get that different plane there? Why it deviates from the plane? Because of repulsion between hydroxy and methoxy group. Okay, right. So the correct order will be meta-methoxyphenol, more than phenol, then comes orthomethoxyphenol, and the last will be paramethoxyphenol. Right, you can confirm the values there. 9.65, 10, and slightly more than 10. Okay, but you can take the value as 10 only. The last one will be 10.21. Okay, so in this way we take acidic nature of phenols. Thank you for watching.